Okay, so I was thinking how to entice you to do exercises for the midterm, and I came up with the following solution. By the way, I'll have extra office hours on Friday, tomorrow, Monday and Tuesday from 2 to 3. But sharp, I really have other things to do, so please come between 2 or 3. Can you make this time? Okay. And tomorrow I will post, say, 10 or 15 problems, and one of them will be on the midterm. Okay. Good try. Okay. So, it's pretty hard actually to come up with decent problems. So sometimes when I cannot come up with a problem where greedy works, I give a problem to show that greedy actually doesn't work. And I was asked to go over one of these problems. So you have a map of cities, right? With their pairwise distances. And the law in Albania is that for every city has to have a school within, say, 10-mile radius. Okay, and given the map of Albania, you have to decide in which cities you will build schools, so that in fact for every city there is a school within whatever 10 miles radius, and the number of schools that you are building is as small as possible. And how would you do it? By greedy strategy, and then show that greedy strategy is not guaranteed to produce optimal solution. What would be a natural strategy by greedy? So every school has to be in one of the cities. You cannot put it in the middle of nowhere.
Choose a place where the maximum number of cities is within 10 kilometers.
Right, so you pick a city so that in the radius of, in a circle of radius 10 miles, there is a largest number of other cities, and then you put a school there, you eliminate all the cities that are covered, and you repeat. Why is this not guaranteed to produce optimal solution? How would you come up with a counter example? What do you think? In such circumstances, greedy always fails in one and the same way. You end up having a redundant choice. So, how would you make greedy fail in this example?
What if you had a place that's about 20 miles long, and you had one city in the middle, and then you had a whole bunch of nothing on the other side, and then
That's right. So you see, it is quite possible that you have a whole bunch of cities here, but then you also have two distant cities, and now your greedy would definitely pick an element from here and put a school around here. So this is 10 miles radius. But these two guys are not covered, and might very well be the case that if you actually that you can cover it with placing a school in a city, say here, and placing a school in a city, say here, and and you cover all of the cities with just these two schools, and the one that you started with turns out to be redundant, right? Because what you really have to put in order to cover these faraway cities actually covers this dense area as well. So starting with the densest part of the map is maybe suboptimal, because this first initial school may turn out to be redundant. You understand this? Right? Because, so the higher concentration is here. So your greedy algorithm would pick a point here and put a school there and say this is the radius of the cities that are of the territory that is covered. But this point here and this point here are outside of that circle. However, if you choose a point close to the border here and another point close to the border here, then it might be well the case that these two circles cover everything and make this initial circle obsolete. So you see, greedy is not guaranteed to work in such circumstances. Okay, let's do another one. So you remember you have on the examples that I gave you, you have certain amount of money X that you have to pay back to the bank, right? But the rules are you have to start with $1 and you have to finish also with $1, and whenever if you pay certain amount Y, then in the next step, so if end payment is Z, then N plus first payment has to be either Z divided by 2, Z, or 2Z. Right, so you can either keep the same or double it or divide it by 2. And you want to pay X in as few installments as possible. So pay X in as few installments as possible. How would you do this problem? You understand the problem? So you have certain amount X, and you have to start with $1, and at each step you are allowed either to keep the same amount, to halve it, or to double it. And you want to pay the whole amount with as few installments as possible. How would you solve this in a greedy manner? Any ideas? Yes?
Could you divide X by 2 and then keep increasing it until you, to keep doubling your values just before you cross the halfway mark? Mm-hmm. And then you go down.
Okay, so depending how you cross the halfway mark, you might overshoot a little bit if, so you have to backtrack. So, okay, so the idea is in the first stage, you start with $1, then you go $2, $4, and so forth until you reach, say, 2 to the k minus 1. And say if the last payment is 2 to the k, you want to choose it so that you have time to decelerate. right? Yes?
Couldn't you just express it in binary?
Sure. Well,
I mean, then you can directly calculate where the solving point is.
well, but you see, it's not quite binary because you accelerate, but you also have to go then, you see, because the sequence has to start with 1 and end
If
with
you
1.
express the logarithm 2 of the value in binary, and then you have you remove one digit of the binary, which
Okay,
is the
so-
way back.
Okay, so that's essentially the solution. So you would do that. So what is the sum? So now you decelerate. By the way, this is how you send probes to a planet. You accelerate, right? And then you have to fire the braking engines, right? Because you don't want to smash. So this is not that unrealistic, you know. This bank has kind of space interest rates, so until you reach 1. So what is the sum here? Well, the sum here is, this is 2 to the k minus 1, and this part will be also 2 to the k minus 1, and here you have another k, so it is 3 times 2 to the k minus 2, and this has to be smaller than x, but you want it so that 3 times 2 to the k plus 1 minus 2 is bigger than x, so that you could not extend for an extra step and still stay in the bound. So what does this, so we are looking largest k such that this holds. Okay, so how do we find that? Well, this tells us that 3 times 2 to the k, it has to be smaller than x plus 2. 2 to the k is smaller than x plus 2 divided by 3. So what is the solution for this? What is k? So k is integer part of what? Of log 2 of x plus 2 divided by 3. Okay. So now you know, once you get k, are you with me? You understand why this is so? Right? Because it simply comes from solving these two constraints, right? This has to be smaller or equal than x. Okay? So now, we find this initial sequence that is as fast as possible. Doubling once again would cause overshot, right? How do we now, what do we do next?
You have to find out which numbers we can produce in these sequences. And then
How do we find that?
So we can try with K1, K2.
No trials. How do you immediately get? So again, you want to do what strategy? So you consider now x minus 3 times, so say this is a k0 that works. So 3 times 2 to the k0 minus 2, right? What do we do with this quantity now? Now we do precisely what this lady suggests, right? We simply represent it, so represent, you see, the idea is now you are again acting in a greedy way. Yeah? These are your powers available, right? So you take as large power of 2 as you can, and you double, you interpolate an extra step, doubling, making 2 of these, right? So this amounts to represent this in binary and repeat the payments wherever for exponents of 2 where you have when you have 1, right? So you simply represent this in binary, and for all the powers of 2 of this leftover, you simply, either in this part of the sequence or that part of the sequence, you simply repeat the value, right? And this is guaranteed to minimize the number of steps. Do we really have to prove that it's minimal? Not really, because clearly higher powers will not work, because if you have 1 extra power, you will be overshooting it. And given this sequence, this is clearly the most efficient way, because you always choose the largest possible power of 2 that you can repeat. So it's really rather simple. But you see, a little bit of arithmetic helps you a lot, because it tells you without, yes?
So if you have a 1, you double that number?
Yes.
And if it's a 0, nothing?
No. If you have 0, nothing, because what does this mean? It means that the leftover is in the form to the k, well, let's call it n1 plus 2 to the n2 plus 2 to the nk, wherever you have 1s, right? And so, but these are precisely the powers that you have that you want to repeat, right? So it's a very clean way of doing this. Any questions? Okay, if not, let's do an FFT so that. So let's compute.
Sorry?
Yes.
Would there be any master theorem things? Because we are not doing any exercise in that.
So what do we conclude from the fact that we are not doing master theorem? I'll let you make a conclusion. There will be no master theorem, but look, you have to only understand master theorem, right? And to know how to apply it. I mean, how can you, if you don't know how to evaluate the runtime of recursive divide and conquer algorithms, what kind of computer scientist are you? Right? We burn such people at stake. So please make sure you understand master theorem. But students, I have to teach it because it's a fundamental tool for analyzing recursive algorithms. But people hate it so much and complain so much that I eventually capitulated and decided not to put it on the exam. Okay, so let's compute discrete Fourier transform of the following sequence. 1, 2, 3, 4, 5, 6, 7, 8. And what is the point here being, just so that you understand, but using kind of FFT by hand, right? Okay, so to do that, we have a sequence of length n. How many roots of unity do we need? If a sequence is of length n, degree of polynomial is 7. So what roots of unity do we need? Of what order? Yeah, so 7 plus 1 is 8. So need omega 8. Now, what is omega 8? Well, let's look. So this is 4 points, and lo and behold, if I insert midpoints here. So what is omega 8? in expanded form, not as a complex exponential, right? This is e to the I times 2 pi divided by n, which is e to the I, what is here, 2 pi divided by 8, which is e to the I pi over 4, which should not be a surprise. But what is omega 8 without, not in just in the form a plus bi? How big is this? This is 1, and this angle is equal to that angle because it's equal to this angle, because it's pi over 4, and this is pi over 4. So if this is x, this will be also x, right? So what is x? What is 2x squared equal to? X squared plus x squared equals to 1, right, by Pythagoras theorem. So what is x? X is square root of 1/2, but this looks very ugly. How do we write this? Well, that's 1 over square root 2, but that's also ugly. This is actually square root divided by 2. We don't like radicals in the denominator whenever we can avoid them. So this is actually just square root 2 divided by 2 plus I times square root 2 divided by 2. Okay? Now, but we are not so how would we compute now? Let me ask you that. How would you compute the powers of the roots of unity? Will you take these to the powers from 1 to 7 or not? How do we compute? Do I compute omega 8 to power 7 as square root 2 divided by 2 plus I times square root 2 divided by 2 to the power 7? Do I compute it this way? No. How do I compute it? Of course, you just go around the circle. There is nothing to compute, right? So let's see, omega 8 is square root 2 divided by 2 plus I times square root 2 divided by 2. So what is omega 8 squared? Well, that's just omega 4, which happens to be what? This is just I, right? Because the square is here, just doubling the argument. So that's I. So what is then omega 8 to the power 3? Exactly, so that will be minus, the real part will be negative, so it's minus square root 2 divided by 2 plus I times square root 2 divided by 2. Omega 8 to the 4th is the same as omega 2. What is omega 2? Minus 1, right? That's this point here. Okay, how about omega 8 to the power 5? Which one is this? It's this one here. What are the coordinates? They are both negative, so it's minus square root 2 divided by 2 minus square root minus I times square root 2 divided by 2. And then what is omega 8 to power 6? What is omega 8 to power 6? That's minus I. You see, there is nothing, so just don't rush. Always think geometrically. If you can see it from the picture, there is nothing to compute. Only now I realize my circle is a little bit eccentric. So what is finally omega 8 to the power 7? So then the real coordinate is positive and imaginary is negative. So that's square square root 2 divided by 2 minus I square root 2 divided by 2. Okay, so now we can do our divide and conquer. So let's do it. So what is the DFT of this sequence? How do we define DFT? DFT is simply DFT of the sequence 1, 2, 3, 4, 5, 6, 7, 8 is simply the sequence of values of P at omega 8 to power K, when K goes between 0 and 7, right? And what is P? So that's simply this sequence. And can you tell me what P of X is equal to? You simply form the polynomial with these values as coefficients. So what will it be? 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus 6x to the 5th plus 7x to the 6th plus 8x to the 7th. So the discrete Fourier transform of a sequence is simply the sequence of values of your polynomial at all the roots of unity of order from 0 to n minus 1, where polynomial has the coefficients that are exactly your sequence. How does Fourier transform, discrete fast Fourier transform work? Let's now, rather than just running, so to speak, the algorithm, which we will do, but let's now kind of also repeat the derivation so that you really understand what's happening. What do we do with this polynomial? How does divide and conquer work? Even and odd powers, that's right. So we write this as 1 plus 3x squared plus 5x to the 4th plus 7x to the 6th plus x times, and then 2 plus 4x squared plus 6x to the 4th plus 8x to the 6th, right? That's divide and conquer. Okay, so what do we do now? What's the next step? How do we reduce the degree of the polynomials? Yes?
I'm so sorry, how did you get the coefficients?
Well, this is just given. I'm telling you, find the FFT of this particular sequence.
Oh, so they are the coefficients.
So whatever is the sequence, we form the corresponding polynomial whose coefficients are exactly these coefficients next to the corresponding power.
Okay.
So this is 0th order, 1st order, 2nd order, and so forth. Good. So you understand, if you have a sequence of numbers, you simply form a corresponding polynomial whose coefficients are precisely your sequence in that order. Okay, so how do we halve the power here? What do we introduce now?
Introduce another variable, say a y.
Exactly. So we now say let x squared be replaced by y. because this will halve the degree of the polynomial. So, what happens then? I'm sorry, I'm totally disorganized on the blackboard. I hope you can. So what do we have now? So if we do that, we get that P of x is equal to 1 plus 3y plus 5y squared plus 7y cubed plus x times, and the second polynomial is 2 plus 4x squared, so plus 4y plus 6y squared plus 8y cubed, right? Yeah. So there we go. The degree of the polynomial has been halved. And not only that, because y stands for x squared, the roots of unity that y will go through will be every other root of unity here, because here they are squared, so you always double the argument. So there will be only half as many roots of unity. So evaluation is now reduced to two polynomials of half degree, evaluated at half as many points. Okay, now we continue with divide and conquer. Let's call this P even of y. Let it be equal to 1 plus 3y plus y squared plus 7y cubed. And P odd of y, let it be 2 plus 4y plus 6y squared plus 8y cubed. So now we continue with divide and conquer. How do I write PE? PE of y is equal to, how do I split it? How do I split each polynomial recursively? What do I always do? Even and odd powers, right? So this is 1 plus 5y squared plus y times 3 plus 7 y squared, which will be equal. If I now say y squared will be a new variable z, this will be equal to 1 plus 5z plus y, and then this will be 3 plus 7z. And in an identical manner, so let's call this will be P even of z, and this will be P even odd of z. Okay, and then in the same manner, I have that PO of y is equal to 2 plus 6y squared plus y, what do we have? Y that multiplies 4 plus y squared, and we get that this is 2 plus 6z, right? Plus y that multiplies 4 plus Did I miss something? 8y squared, that's good. 8z. Okay, now theoretically we could split this into even and odd powers, but it makes no sense, right? We will simply stop at 2 and use roots of order 2, which are just, what are roots of order 2? How many roots of unity of order 2 are there? Which one are they? 1 and minus 1. So now all what we have to do is, now we do it recursively, right? We will always evaluate this polynomial and multiply this part with the corresponding root of unity. Okay, let's see. So what is this? This is P odd and then even, and this here is P odd, odd. Oh God, we have 2 and P. No scatological intention whatsoever, it's pure coincidence. Okay, so let's see now. So what is, now we do, what is dft of the first polynomial, PEE? dft of the sequence 1, 5. What is this? Well, this is simply the sequence of, what is the polynomial here? It's simply PEE of 1, PEE at minus 1, simply because omega 2 is minus 1, omega 2 squared is 1, of course. So, and we always start clockwise from 1. Okay, so what is this? Well, this